My name is Steve Mackay, and I'm going to be doing a quick presentation on the key elements of the AS3000 wiring standards, some of the recent changes. So, very quick whistle-stop tour. My name is Steve Mackay, as I said, Dean of Engineering, and focus mainly industrial automation, but I've done quite a lot of electrical engineering work as well. So I really just want to spend a few minutes talking about the electrical wiring standards, AS3000 2007, which is probably one of the critical underpinnings of any engineer, whether it's electrical, mechanical, in Australia, New Zealand, and of course, if you're a technologist, technician, or tradie, this is probably the main building block. If you understand this, you're away. And one of the biggest challenges, of course, is to ensure that anyone coming from overseas is very familiar with this standard. It's actually quite amusing. As a training organisation, we actually run these courses within the States because a lot of American firms are building equipment to not NEC standards, but to the AS3000 rules. So, this is an extract from our course, which runs over 2 days. So I just want to give you a quick intro to the structure of the standard and sort of a kick-off on distribution, one of the key modules. So this is just the structure of the course, which I'm not going to worry about. That's over 2 days. And we then look at the regulations. Obviously, the whole idea of regulations is to give everyone the same standards, which means you can interchange stuff, and probably, I'd say, probably more important, standards give you a nice, warm, fuzzy feeling about safety. If you all have the same standards, when you're working on a switchboard, you can be guaranteed if it's AS3000 and it's been complied with, you're going to be working in a standardized, safe environment. So consistent quality and performance, very important, especially in today's competitive world. You don't want to be undercut by some shonky outfit who doesn't use the AS3000. So that's why it's criminal if you have a breach of the standards where there could be safety problems. The main objective is define the minimum requirements. So obviously, if you're a good supplier or vendor, you'll go beyond the minimum. And the design, construction, testing all electrical equipment in a safe manner, so to protect you from electrical shock and obviously fire, which is often not thought about as much. In fact, the US NEC code is actually driven by the National Fire Protection Agency. It's a wiring standard, but it's driven by them. And obviously, new installations as well as modifications, additions to existing ones. And I must say, existing installations are a special challenge because you've got to try and make sure, without being too nasty, about upgrading to keep up to the modern standards. For example, RCDs, you need to put extra ones in a household. You need to do it in such a way that it can be done over a period of a few years and can be done in a guaranteed way. So it's quite a challenge for the standard to ensure it's done. How does the AS3000 ensure safety? These are the practices we follow for protection against risks and hazards, and the requirements made by the system, equipment, accessories to meet these, and obviously mandatory verification and testing to ensure installations comply with the minimum safety requirements. So typical application areas, all types of premises, looking at safety of workplaces, safe design and construction of buildings, like the Building Code of Australia or New Zealand Building Code, electricity generation, transmission, distribution is a very big area, safe connection to electricity distribution systems, and obviously the other area is qualification of electrical workers and the licensing thereof. This one's 12th of November 2007, so it's quite a few years ago, and believe me, it's taken a lot of work to get to that stage. The standard has a lot of extra bits, increased registration, As we all know, engineering professionals, technologists love diagrams far better than text. And there's two parts: scope, application, fundamental principles, and in part two, and obviously establish the deemed to comply status 3018 relating to simple domestic applications. Some of the changes, here's a list of the sort of typical changes: illustration of normal alternative location of the current devices and its emission, single main switch for single domestic, so quite a strong, obviously, focus on the consumer, domestic appliances. Arc flash has become a very big area. There actually isn't a standard for arc flash protection yet in Australia, although there is one in the US driven by the IEEE, but there will be soon a arc flash standard. So very important. Arc flash is the cause of a lot of disasters. These residual current devices I mentioned earlier on, very important for circuits up to 20 amps. Maximum 3 circuits connected to any one RCD. And obviously a voltage drop of up to 7% when the substation is located within the premises. And there's a few additional appendices. The contents, as I said, part 1, to align with IEC 60364 for essential safety. Part 2, practices to be followed to achieve safety. So safety is obviously an overriding issue. And failure to comply with the work method provision in Part 2 would breach high-level safety conditions of Part 1. And then obviously testing and inspection provisions updated and aligned with the 3017. And the issue to try and ensure compliance is periodic inspections. So Section 1, scope, application and fundamental principles. Definitions of various electrical terms, so you sort of get everything set up for interpretation of the document. So Section 1 is very important to give all the fundamental definitions, principles of protection, basic requirements for new installations, additions and modifications to an existing installation, which is quite challenging. Section 2 is general arrangement, control and protection, so focusing on switchgear and control gear, fault conditions, coordination protection devices, and obviously design, selection, installation of switchboards. Section 3 is selection and installation of a wiring system, so protection against external influences, environmental conditions, all the way through to, it's quite a list here, I'm not going to run through each one of them, meets current carrying capacity, identification of safety maintenance and fire protection measures. Fire is obviously a hazard we want to try and avoid. Section 4 is selection and installation of appliances and accessories, such as motors, transformers, capacitors, heating systems, lighting systems, UPS, and standby systems. Obviously, UPSs and standby sources are pretty important these days, especially with computer-based technology, and obviously critical hospitals. It's very important we have a standard approach there. So protection against physical injury, thermal effects, heating, safe and reliable circuit connection, and proper isolation, switching, and protection devices and their features. Section 5 is earthing, or as our American friends call it, grounding, and earthing conductors. So very interesting section, actually. And again, there's a whole slew of associated standards relating to earthing, which are not only in the AS3000, and should be known as well. Recommended earthing resistance values, mechanical protection, and sizing and selection of earthing electrodes and conductors. Now again, it's not going to go into exhaustive detail. You need to refer to probably some of the IEEE standards, but again, very interesting area. Section 7 is special electrical installations, safety services, generation systems, electrical separation systems, extra low voltage, etc. And I missed out Section 6, which is damp situations, should be neglected, safety concerns in damp areas. So very important, obviously, electricity in damp areas is extremely dangerous. And unfortunately, we've got lots of saunas today and lots of showers, pools, etc. Very important. In fact, in the office, we just had to put another floor in. Massive amount of water accumulating around air conditioner units. So again, very important to have a standard approach. Section 8, verification. So this looks at minimum inspection and test procedures to check. Checklists, mandatory tests, sequence of tests. So very important section. And then there's a whole bunch of appendices as well. So again, very important to look at the appendices. So it's a very well designed standard, all the way to degrees of protection, IP classification. So for example, spraying water on an electrical switchboard. Can you do that? How does it need to be protected? Classification of wiring systems, symbols used. There's even a shock survival guide for Australia and New Zealand. It's very hard for two countries to mesh in their different approaches, and it's actually to the credit of the standards body that they've got both Australia and New Zealand fairly well aligned. It'd be hard not to. There's so much into marriage between the two countries in terms of electrical activity and obviously mechanical. In this module, this is the first module, is the electrical distribution system. So I just want to briefly run through some of the issues there so you can just get a flavor for the whole standard. So in this we look at AC/DC systems, polyphase, vectorial representations, importance of earthing, etc. Energy sources range from conventional energy sources and then obviously non-conventional renewable energy, which is obviously the big driving force today. And solar power and wind power obviously put some special challenges on the grid, as we all know, but that's a topic for another day. So initial distribution systems, you've got a source and a load. Looks like high school physics. And then, of course, you've got the conductors that are carrying the current from source to load. Distribution systems today, hundreds of large systems, and obviously quite a range. AC/DC power, interesting enough, DC power is perhaps growing in importance compared to what it was 50 years ago. And obviously the big challenge with AC is it's got to be three-phase, and we use the vectorial representation for these sinusoidal waveforms. So here we have phases. It gets quite interesting, this. As you know, you have the rotation of the phases, as we put there. Phase B follows phase A. So you've got phase B follows phase A. So you get this rotation going around like that. And the idea is that the phases rotate around A. So if you're standing over here, you see the phases passing you, so in that direction. Obviously, if it's going in the opposite direction to the one I've sketched there, your motor will be rotating in the reverse direction. And that just requires A and B connections to be transposed. So it's quite a good way to represent stuff and everything, and it's quite useful to look at three-phase systems like this. Here's your star connection, neutral, and here's your delta connection. Just bear in mind here, it's always a bit of a challenge this, but if you look at the star connection, your line voltage, if you look at V line, is actually related to the phase voltages. The phase voltages across there. So, for example, the phase voltage is equal to line voltage divided by √3. Whereas over here, of course, you've got your phase voltage equal to your line voltage. And then I can also go through the line currents, which are the opposite way around. But we're not going to look at that now. Protection, obviously, need for protection. Person's livestock, very important. Need for earthing, and it's actually a really interesting area, earthing. We need to keep all live systems at or near ground zero potential. So the idea that means a lower shock, but I'm probably talking to the converted here. so I don't go into detail there. So obviously the idea is it's good for easy fault detection using earth as a path for flow of currents from the fault point to the source, thus preventing things we dread, which are catastrophic accidents. Sort of definitions, which again are defined in the standard, are the earth, conductive mass of the earth, protective earthing, which is connection of exposed conductive parts of insulation to the earth through earthing terminals to protect against direct and indirect contacts. This is opposed to functional earthing, which is earth connections for proper functioning of equipment and not providing safety. And then earth terminal, the terminal bar provided for the connection of protective conductors, bonding conductors, and functional earthing conductors to the earth. So those terms we use, and you need to know them. Here's a typical example of a fault current. Here's the load current, which is what you hope is happening. And of course, you've got sort of current going here, earth fault, and you've got dispersed flow of fault current through here. Obviously, you want to try and do this in a controlled way where possible. So earthing is probably a critical thing with anything to do with safety. Protective earthing functions to reduce electric shock hazards to personnel, as I mentioned. Very important. Common electrical hazards are thermal effects, so you need to have a way of protecting against that, and this is all defined in the standard. Overcurrents, overvoltage, undervoltage. Undervoltage is an interesting hazard, but again, we want to try and operate to define criteria. So, in essence, this just gives you a quick rundown on AS3000 standard, just a quick overview of what it's structured as, and then the first sort of module. So hopefully, any questions, ask me, Steve Mackay, or drop me an email. I'll be delighted to respond. Thank you very, very much for listening into this short dissertation. Hope it wasn't